In 10.7, we're going to introduce polar coordinates. Polar coordinates are another way to graph points and graphs and other things, just using a different system than the rectangular coordinates, the x, y that you are used to. Okay, so when we write an ordered pair for a polar coordinate, it's r comma theta, where r is the directed distance from O to P. P is the point. Theta is a directed angle counterclockwise from the polar axis to segment OP. Okay, let me figure out my point. Okay, let me pick a point. I'm going to randomly place a point. I'm just putting it in quadrant 1 because it's easy. Okay, R is the directed distance from O to P. When they say O, they're talking about the origin. So the directed distance R is from here to here. Okay, theta is the directed angle counterclockwise from the polar axis to segment OP. The polar axis is this one right here. So theta is the directed angle, meaning it matters whether it's positive or negative. This is the positive direction. So this should be very similar to the standard form or standard position on the unit circle where we started from the positive x-axis and going in the positive direction was up towards OP. Okay, so this is how we, on a polar graph, it looks like this. Each of these lines represents r equals 1, r equals 2, r equals 3, 4, 5, and so on. So I can make this circle as many points as I want. Let me see. This is 0, just like on the unit circle. This is pi over 2, just like on the unit circle. Where is pi? Pi is over here. Okay, depending on how this is divided up into 1, 2, 3, 4, 5, 6 sections, which means each of these represent pi over 6. So this would be pi over 6, 2 pi over 6 is pi over 3, and so on. So it's very similar to the unit circle. So I'm going to go ahead and plot the first point. Okay, so if I look at A is 2 comma pi over 3. So first let me find the pi over 3 line. Okay, this is the direction I want to go in. Okay, and I want to travel a directed distance of positive 2 from O. So if I start here from O and I go 2 units, 1, 2, this is point A here. It's 2 units along the pi over 3 line, and the line doesn't need to be there. Actually, maybe I should erase the line so you don't think it's supposed to. I'll do it on the next one. Okay, so now let me look at B. B is 3 comma negative pi over 6. So first let me find the negative pi over 6 line. If that's positive pi over 6, then negative pi over 6 is down here. Okay, so along this line in this direction, R is 3, so I'm going to travel 3 units along this line. 1, 2, 3. So point B is right here, and it does represent a point, which was why on A I shouldn't have written that line. Okay, one more for C. R is negative 4, theta is pi over 2, so pi over 2 is along this line. But from O, I want to travel negative 4 units. So if I'm going negative 4 units, I'm actually going to go backwards. 1, 2, 3, 4 units. So this is point C down here. Now, each of these ordered pairs for the polar coordinates are not unique. So for example, for C, I could have also called this one positive 4 comma 3 pi over 2, and that would have been the same exact point in the polar plane. Okay, because each ordered pair is not unique, shouldn't be called an ordered pair, each polar coordinate is not unique, I could find a different representation for each point. So for example, for 2 pi over 3, which was my point A, it was located at this location. But that's not the only way I could have named it. So I'm going to find 3 additional representations for the same exact point with the restriction that negative 2 pi is less than theta is less than 2 pi. So there's a couple things I can do. I can change the R, or I can change the angle. So let's say I'm going to keep the R the same. Okay, right here it's 2 comma pi over 3. I could name pi over 3 in a different way because I can go from negative 2 pi. From here, I could go backwards until I get to this line and give it the same name, but it would be a coterminal location. So sometimes you can just look at it and say, okay, that's going to be negative 5 pi over 3. If you like formulas, which many of you do, I'm going to start with pi over 3. And then remember, I want a coterminal angle. but I want it to be negative, so I'm going to subtract 2 pi. Remember, that's coterminal. It has the same ordered pair. It's an equivalent theta on the unit circle. If I do pi over 3 minus 6 pi over 3, I get negative 5 pi over 3. And if I graph that, I would get the same exact point as point A. Okay, now I could also change the r, just like we saw with the point C. I could have used negative 4 with pi over 2. I could have used positive 4 with 3 pi over 2. So let me try it with negative 2, and then I'm going to think about how that would change the point. Okay, let's say I called it in negative 2. Okay, now if it was negative 2r, then I want it to go, this would be going backwards, which means I'm actually lying along this angle over here. So if I went on this angle, but I went negative 2, I would be actually back at point A again. So how do I get over to this angle? Well, this is half a circle away, so I could add pi or I could subtract pi to find the angle on the opposite side. So let's say I add pi. Okay, pi over 3 plus 3 pi over 3 is 4 pi over 3. Okay, let me check and make sure this is the same point as point A. Where is it? Pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3 is along this line. If I travel negative 2 units along this line, I go back 2 and I end up at A again. Okay, now let me find another point using r is negative 2. Okay, how about if I do pi over 3 and I go back pi? It's still going to take me to the other side of the circle, just in the opposite direction. So pi over 3 minus 3 pi over 3 is negative 2 pi over 3. And I'm going to just look at the graph and make sure that that appears to be equivalent. Okay, so from here, this is negative pi over 3. This is negative 2 pi over 3. So if I travel along this line, this is negative 2 pi over 3, but I'm going negative 2 units from O, so I'm going to go back 2, so I still end up at point A. So all 4 of these representations are representing the exact same point, and if they had not restricted my theta, I could have found even more points. Because you can represent points using polar coordinates or rectangular form, sometimes you might want to switch from one to the other, depending on what you're trying to analyze on the graph. So how we convert it is using the formulas we remember from trig, actually. So if you recall, x is equivalent to the cosine of theta on the unit circle, but that's when the radius is 1. So if I want to find the x, it's r cosine theta. The y is r sine theta, just like in the unit circle, well, when we did trig, actually. To find the tangent of theta, that's still y over x, or sine over cosine. And then x squared plus y squared equals r squared is still true, which was just like it was when we did the trig in chapter 4 or something like that. Okay, so this is 2 to pi over 3, which is the same point we've been looking at for quite a bit now. Okay, but say I want to change it to rectangular form, meaning instead of this being r theta, I want it to be x comma y. Maybe just because it's easier for me to graph. Okay, so if I want it to be x comma y, to find the x is going to be r cosine theta. What's r? R is 2 cosine theta. If I want the y is going to be r sine theta. The r is 2. The theta is pi over 3. Then I am going to simplify this. What is the cosine of pi over 3? The cosine of pi over 3 is 1/2. The sine of pi over 3 is root 3 over 2. Yes, you still need to know your unit circle. So 1 comma root 3 would represent the same point in rectangular form. Let me look back at my graph and see if that seems reasonable. Okay, so if I was at point A, if I went right 1, that matches. Up root 3, that's entirely possible. So if I was graphing it in the xy plane, it would still represent point A. This would just be in rectangular coordinates. Now I'm going to go the opposite way. It says convert to polar coordinates, so I want my answer to be r theta, but they're giving it to me as xy. So this is my x, and this is my y. So I need to figure out what the r is, and I need to figure out what the theta is, and then I can rewrite my point. Let's see. Let me do r first, because r is straightforward. R squared equals x squared plus y squared. X squared, 5 root 3. 5 root 3 squared plus 5 squared. 5 root 3 squared, 5 squared is 25, root 3 squared is 3, so 25 times 3. So r squared is 100, so r is going to be 10. Okay, now to get the theta value, I'm going to use the fact that tangent of theta equals y over x. Okay, now I want to figure out where the tangent of theta is 1 over root 3. I'm going to have to consider the quadrant this is in because there is more than one location on the unit circle where this happens. Because this is positive and positive, this must be in quadrant 1. So I'm only going to consider the theta values in quadrant 1. Remember, this is y over x. So think of your unit circle. The one where the y is low is 1/2. X is root 3 over 2. That's going to be at pi over 6 while I'm in quadrant 1. Okay, so my polar coordinates are going to be r, comma, theta. Okay, and remember I picked that theta because it's in quadrant 1. Now remember, this is not a unique representation, so you could write it in another way, although this is the most straightforward way. Okay, let's do one more like that because there's a little more to keep in mind. Okay, so again, they gave me it in rectangular coordinates. So they've given me the x and the y, and I happen to notice this is in quadrant 2, which I'll keep in mind for later. Okay, if I want to find r squared equals x squared plus y squared. So r is the square root of 2. Okay, let me find theta so I can complete my ordered pair or my polar coordinates. So the tangent of theta equals y over x. Okay, that's going to be at one of those pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Okay, so if I'm in quadrant 2, that must be at 3 pi over 4. So for my polar coordinates, I'm going to do r comma theta, where r is root 2 and theta is 3 pi over 4. And again, not unique, but this is the most straightforward answer. Sometimes they do give you a restriction on theta, in which case you would be careful. Okay, the last thing we're going to do is convert rectangular equations to polar equations and polar equations to rectangular equations. Rectangular equations have x and y in it. That's the one we're used to. Now, polar equations, we haven't graphed polar functions yet, so you don't really know what they look like. But the equation normally ends up like r equals. Sometimes it's r squared equals if we can't simplify it, or we get theta equals. So that's the format we're going to go for. So we're going to try to convert these, and we're going to use the identities that were written on previously in your notes. Okay, so this is in rectangular form because it has x and y in it. My goal is to turn it into this, this, or this. Okay, now I want to look and see if I recognize anything. So if you look at that list of identities on the other page, you should see one that says x squared plus y squared is equal to r squared. So I can rewrite this as r squared equals 49. Now, whenever possible, you do need to get rid of the r. We don't want to leave r squared there unless we have to leave r squared there. Okay, now if I square root both sides, I should get plus or minus 7. But because polar equations are interesting, I'm just going to put positive 7. That doesn't mean r can't equal negative 7. I could also put r equals negative 7, but I don't need to put both. And the reason I don't have to put both is, don't write this down. We're going to learn how to graph these soon. But if I go to r is 7, let's say I go out 7 units. Every unit where r is 7 is all these points out here. Now if I say r is negative 7, I'm just going backwards 7 units, and then I'm marking all the points that are out here. So these are actually totally equivalent equations. They produce the same exact polar function. Okay, let's try the next one. Okay, B, I see y. Let's see, if you look back at the previous page to see what y equals to r sine theta. X squared, that doesn't have a special one, but x is r cosine theta, and I could square the entire thing. Okay, so r sine theta equals, let me distribute this, r squared cosine squared theta. Okay, now I'm trying to get it to say r equals. So I'm going to cancel an r, which means I'm going to divide by r. Now you can never ever divide by x. That's like my greatest pet peeve. But because r is non-zero in a polar equation, we're allowed to divide by r. but only here. Don't do it on any xy rectangular equation. Okay, so if I do that, I get r cosine squared theta. Okay, I still want to isolate the r, so I'm going to go ahead and divide by cosine squared. R equals, I'm going to split this up. So I'm going to do sine over cosine times 1 over cosine, because when possible, I try to get rid of the fractions just like we did on trig identities. Okay, so this is my best equation. It's r equals tangent theta times secant theta. And that's representing this lovely parabola, but in polar equation land. Okay, let's do one more. It says y equals negative x. Okay, now if you check your list of identities again, y is r sine theta equals negative, what is x is r cosine theta. Okay, because this is a crazy world where we can divide by r, the r's are going to cancel. Again, only in polar land, not in normal land. Okay, now I just have thetas, so let's try to get, let's divide by cosine theta. This is not the only way to do it, but now I'm going to try to go for theta equals, since I don't have an r anymore. Okay, now tangent theta equals negative 1. I wanted to say theta equals. Okay, now theta equals, where's the tangent negative 1? Well, it could be at 3 pi over 4. It could be at negative 5 pi over 4. It could be at 11 pi over 4. All of those are equivalent answers. So this is one possible answer, but again, it's not unique. So any of the other answers I also said, those would also work. And I do have it in the form of theta equals, which is a good polar equation. Okay, lastly, we're going to convert these polar equations, which are in terms of r or theta, into a rectangular equation, meaning the result will have only x and y in it. Sometimes these require a little more creativity. Okay, I see r equals 4. There is nothing from those formulas that says r equals. So I'm going to have to square both sides because there is an r squared equals on the list of formulas, and that's going to help me create something I can work with. Okay, so I get r squared equals 16. Because I now have r squared, I can substitute x squared plus y squared for r squared, and I get x squared plus y squared equals 16. Okay, I'm just going to look at this for a second. If in rectangular form, this would represent a circle with center 0 and a radius of 4. And if you look at the original equation, it also represented a circle with a radius of 4. So these are equivalent equations, just one is expressed in terms of polar coordinates and the other one's expressed in terms of rectangular coordinates. Okay, now for b, it says theta equals 2 pi over 3. Okay, the only equation that has a theta in it from the list of formulas that we've been using is tangent theta, which equals y over x. Okay, and I'm using that because it's the only equation that has theta by itself. Okay, now they tell me that theta equals 2 pi over 3, so I'm going to substitute in tangent of 2 pi over 3 equals y over x. Now the tangent of 2 pi over 3 I do know because that's at negative 1/2 root 3 over 2. So that's going to be negative root 3 equals y over x. And then I'm just going to multiply the x to the other side so it looks more like some kind of standard form. Okay, so this actually represents a line with a slope of negative root 3. You don't have to sketch it. I'm going to sketch it real quick. Okay, we haven't learned how to graph this yet, but if I graphed, where is negative 2 pi over 3 is somewhere over here. If I drew the line theta equals 2 pi over 3, it would actually look like this. And if I graph the line y equals negative root 3x, it would have a slope of negative root 3 over 1, which could very well look something like this. Okay, let me look at the next one. C is r equals 5 secant theta. I'm going to rewrite secant as 5 over cosine. And I'll look and see if I can do something else with this. I'm going to go ahead and multiply the cosine to the side with r. So I'll get r cosine theta equals 5. Now r cosine theta I know equals to x. So now I get x equals 5, which actually means if I tried to graph this, try to graph it on Desmos. I'll get a vertical line going through the 5, and it really will work. Okay, the last one, let's see. It says r equals 7 sine theta. If this said r sine theta, that would be great, but I don't see how I can move the r so it's multiplied. It would end up being divided. Because of that, I'm going to try to create an r squared on the left side, because at least I can do something with that. Now, I'm going to create the r squared by timesing by r. I'm going to show you why. Let me rewrite this, 7r sine theta. Okay, now if I multiply by r, I get r squared equals 7r sine theta. R squared, I know, is equal to x squared plus y squared. Now r sine theta is actually equal to y, which means 7r sine theta equals 7y. You could leave your equation like that. I'm going to move the 7y to the other side because your book often does that. Okay, but this is in rectangular form. If I actually tried to solve it out, it would create some kind of circle, but the center is not at 0, 0. Okay, but now it is in rectangular form.